code goes to the instruction decoding unit. Instruction decoding ID for instruction decoding unit, ID instruction decoding. So when it goes to instruction decoding unit, so it does basic operations, right? So this is transfer, data transfer. Similarly, you can have okay, so these two I have to delete actually. So then you can have basic operations as you said. So we can have like this logical operations. Like XOR and there could be invert not, or so these are logical operations. That means if you write XOR one register with another register, the content of R1 R2 will be XORed and then it will be replaced in R1. Something like this. Similarly, arithmetic operations like add, subtract, multiply, divide. Then program control. Program control means if the, so as you know, in this von Neumann architecture, the code is actually assembly codes are written in binary forms. One code, second code, third code, like that. So you can write a code to jump or branch. So like branch instructions, branch, call, jump. So all these instructions will try to change the order of the execution. That means if you write a jump to a particular address, it might go to somewhere else and start executing. So branch, call, jump, program control. Then there could be instructions like, you know, memory related instructions, load store instructions. I have already discussed about them. Then IO related, IO device or IO interface, like out, in, things like that. So basically, assembly language codes are very fundamental codes which does this data transfer, logical and arithmetic operations, program control, things like that. So this AVR Atmega 32. So if you look at this Atmega 32 controller, so I have already discussed about your architecture of the Atmega 32 controller. Just give me a second. So this was the architecture, basic architecture of the Atmega 32. We discussed last class. I'm sure you have remembered them. Otherwise, I'm just for your sake of recall. So this I am putting here. So this is your Atmega 32. So there are 32 general purpose registers. There is an arithmetic logic unit, and there is a flash or program memory. So here you put the instruction code here. So the program counter, which is a register, which keeps tracks of the program memory. Then it comes to instruction register. When instruction gets decoded, then there is timing and control. So the instructions, there is a arithmetic logic unit which is tightly coupled with the general purpose registers. So this is where the assembly language. So this assembly language code, basically the assembly language coding, assembly language, which is basically the machine language for the processor, and the processor architecture They are one and same. Basically, the processor this decides this and this decides this. So whenever you have a code, assembly code, so we have this RISC instructions. That means reduced instruction set computing. That means very, very fundamental instructions which can be executed in one clock cycles. So basically this will take one clock cycle, maximum execution. So this architecture has a specific assembly code. So let's discuss that assembly code. So let me show you this table directly, which will you guys can note down the different type of instructions, and I will tell you how to read this. So this is the assembly manual. I can put it here so that it will be easier for you. So let's see the first few instructions. How to read this instruction. This is the instruction manual. You can see there are few headings like called mnemonics, operands, description, operation, and flags. Each instruction is associated with an addressing board. You please write down the addressing board. So for example, this is RD, RR. RD is one register, RR is one register. So this is called add without carry. That means RD and RR will be added and it will be replaced by RD. So this sort of instruction is called register addressing. That means it is register direct addressing. It is doing register direct addressing. That means the data, how it is accessing data, that means it is specifying the register where the data is stored. Is it clear? Hemant, is it clear? Mumbidim Hemant?
Yes, sir.
Ah.
Yes, sir.
So add without carry means there is no carry flag. And what about these flags? These flags are all affected. Z for 0, C for carry, N for negative, V for overflow. What is H? What is H flag? Arundhati Naskar. Arundhati.
Yes, sir.
What is H flag?
I don't know it.
Half carry. You don't know, you read. Refer to your notes. H for half carry. Okay. So why half carry is used? Angana? Angana, why half carry is used? Angana, are you there? Angan? Angana or Angan? Not there. Puja, please put a red mark on Angana Mandal. Why you are there? You have to give an explanation. Otherwise, I shall not allow you next time. Omkar Modi, tell me what is the use of a half carry? Half carry means there is, this is 8 bit, this is 8 bit. Okay. This is 0 to 3, then 4, 5 to 7. So 0 to 3. So the half carry means the carry which is generated here. This is
Yes,
8.
sir.
So what is the use of this half carry? Find out. Okay. It is used in binary coded decimals. What is binary coded decimals? When you use 4-bit representation for binary coded decimals. Okay. So this is, please find out and answer me next class. So then ADC is for add with carry. RDRR and the carry flag is added. So why you need add with carry? Hanisha? Obil Seti Hanisha?
Yes, sir.
Why do you need this add with carry?
Sometimes we need to add the carry which is from the before operations.
Why? When? In which case?
Suppose if we are taking, suppose if we are not doing the edge starting and we are doing in the middle, the operation in the middle of some particular set of operations, then
No.
we
Whenever
we
you are
need to
adding more
add.
than 8 bits,
Yes.
if you add 8 bits, fine. But if you add 16-bit numbers, so first you add this
First 8 bits.
LSB significant byte, the carry, then with carry you add the MSB.
Yes.
This is LSB, list significant byte. So you add them, whatever is the carry, you add with MSBs. Okay, so second one will be add with carry. Okay.
Yes.
Similarly, these flags should be accepted. And the clock, number of clock cycles is 1, 1. Clock cycles, you understand? What do you mean by clock cycles?
Clock cycles means.
Vaibhav Ankush. Mesram
Yes,
Vaibhav
sir.
Ankush. What do you mean by
Yes,
clock
sir.
cycles? Why the clock cycle is mentioned? Last row is, last column is clock cycles.
Sir, I don't know.
In this particular block architecture, you see everything is running with synchronization with the clock like this. A clock weapon goes like this, 0 1 0 1 like that, 0 1 0 1 0 1. So whenever the clock is, so every program counter addresses the program memory or flash memory in one clock. Data is, instruction code comes to the instruction register, it is decoded, then finally instructions are done. लेसन में हो क्या? कहीं पे जा रहे हो क्या? Anyway, ठीक है. So everything is running in a clock cycle. So in one clock cycle, the instruction is brought from the memory, decoded and executed. So that gives you the clock cycle. So this shows the number of clock cycles. So add and add with carry, they will be done in one clock cycle. Okay. So the next instruction is add immediate to word. But word means what? There is a K is a byte, a number is specified. K is, so this is called immediate addressing. These are called register direct addressing. This is immediate. Immediate means the data is specified in the instruction. Add ADIW. Add immediate to word. That means RD.
So,
Yes.
so like the clock cycles mentioned basically means that if I have to perform this operation, I mean if I use that particular command, then it will take one whole cycle to complete.
Yeah, it will take one clock cycle. So if you write a lot of codes, assembly codes from this table, you can find out how much time, exact time it will take. This helps you a lot because you can minimize the program execution time by looking at the clock cycles. That means in one clock cycle, the instruction will be coming from the memory. It will be decoded and executed. Okay, is that clear?
Yes. So like just a doubt, like while computing, if it so happens that the command was like generated when it was say a positive edge of the clock cycle, then it means that for the next like till the next positive edge appears, the same command will be executed.
Yeah, so that is the time where the processor will be occupied to execute that instruction. got it? So here immediate to ward. Ward here means it is 16 bit. Okay, not 8 bit. ADIW means add immediate to ward. So RD is the register. RD could be R1, R2, R3 up to 32 registers are there. R0 to R31. So RD plus 1 and RD together. If it is R1, let's say, that means R1, R2 together will be taken as one word. It will be added with K. Then it will be replaced by RD plus 1 and RD. That means this register, suppose RD is R1, then RD plus 1 is R2. So R1 and R2 will be taken together as 16 bit. It will be added with a 16 bit number. Then this whole thing will be replaced by the result. In this case, it takes 2 clock cycles. Why so 2 clock cycles? Because this instruction is not 8 bits. These instructions are not 8 bits, but this instruction is 16 bit. Because there is a instruction and there is a word. So therefore, when you want to read this instruction, it will itself need an additional clock cycle. Therefore, it is 2 clock cycles. Is it clear? Meena, Anshul Kumar Meena, is it clear to you? Anshul Meena. अरे अंशुल मीना तुम है या नहीं हो? अंशुल मीना को थोड़ा ये दो. Actually, these people, if you are not coming to the class, fine, but don't waste your time. Okay, Khusagra Khular, tell me, is it understood to you? Khular. Khular, are you there or not? उसको भी रेड मार्क डालो. जंगम दिनेश.
Yes, sir.
Tell me, have you understood this add immediate with word?
Yes, sir.
What does it do?
Sir, it will add a constant.
Constant is 16 bit or 8 bit? It could be 16 bit, it could be 8 bit. Okay. It is a 16 bit addition. Can you see this? Please be attentive to this. Because this is what is your exam. You have to write assembly codes. You have to all write assembly codes, explain them. That is your job. Embedded system class will not leave you whether you attend the class or not, but we have 7-8 teachers to test your learning. You have to learn. There is no other way. Because this is what is the main thing in your electrical engineering.
Sir, but
Yes.
in AVR the registers are of 8 bit. So
Yes. So this
how can it be 16 bit?
RD plus 1 RD, they are paired. You are not seeing this. That's what I told repeatedly. They'll be paired to
sir.
make 16 bit word. Okay.
Okay, okay, sir. Okay, got it.
So therefore,
Sir,
clock cycles. Yes.
so like if the addition is 16 bit, like so like which like R2 among RD plus 1 and RD, like which register comprises the MSB part, like and which
RD
part
plus
like,
1, obviously RD plus 1 will be MSB, RD will be LSB. Okay.
okay, sir.
All right. So
And the value is
value,
also stored in RD plus 1 and RD, like
yes,
in that.
that's the meaning of this instruction. So RD plus 1 RD will be replaced. Then subtract without carry, then subtract immediate. You can see subtract without carry, 1 clock cycle. Subtract immediate is 8 bit subtraction. You can see RD sub I. SBC subtract with borrow or carry. That means carry flag is involved, required for more than 8 bit subtraction. SBCI subtract immediate with carry. SBI will subtract immediately word. Whenever there is word thing, there is 2 clock cycle. Then and immediate. You can keep on seeing this or so. See the whole thing. I am now uploading to your this thing. You open it so that we can quickly go through it. You please open. Now I'm uploading it to your. I'm just uploading it. Okay. You guys open it, and you can put your some marks if necessary. Already it was there. Earlier assembly language guide was there. So once again I am uploading. So you can download this and open. Okay, I shall ask, please open it. I shall ask you, one of you to tell me. Suppose this instruction. Mul, RD and RR. What it? Amrita Chaurasia, please explain this instruction. Amrita Chaurasia. Amrita Chaurasia, are you there?
Yes, sir, I'm there.
Yeah, please explain this instruction. Which on your
Yeah,
video?
just a minute. It's
Yeah,
yeah.
you take your time.
Yeah, so going by the trend of ADD and subtract, RD and RB registered will be multiplied and stored into RD.
No, you please check. That's what you are not doing. That's what.
Yeah, I mean, it's opening. It's not yet open.
Okay, will be replaced. It will go to where the results will go.
RD.
No, go to R1 and R0. Because it's a 16-bit. This 8-bit multiplied, it will be maximum 16 bits. So it will come here. Okay.
Yeah. Now I can see in the sheet. It got opened.
This is the unsigned multiplication. Which flag will be affected?
C carry.
Only carry flag will be affected, and it could be sometimes 2 cycles or sometimes 1 cycle. Okay. Sometimes
So can you explain how it's? I mean,
it's
varying.
generally some microcontrollers it is 1 cycle, but it is not in basic microcontrollers. Baseline it is 2 cycle, but advanced microcontrollers it become 1 cycle. Okay.
Okay, sir.
So this is 2 cycle. Okay. Thank you very much.
Thank you, sir.
Okay. So let's.
Sir,
Yeah.
so like in this multiplication, the result will be stored in like R1 R0 registers, right? So like
Yes.
like previously, if there is some value loaded in R1 and R0, then these
That
values
will
will
be
be
overrated. That will be overrated.
So if we want some other register to have that value, we have to then later, I mean, give that value, assign the value of R1 and R0 to that particular register. Like.
No. R1, R0, whatever is there, it will be overwritten. The multiplication result will come here after the execution of the instruction. That's all. What is your question?
So if I want some other register to have the value of multiplication.
No, multiplication is a hardware thing which is hardwired to here.
Okay.
It's not like addition and subtraction where you can change the destination, but here the destination is fixed.
Okay.
Right. Okay. Now let's somebody tell me. Please be attentive. I will call someone to explain me this jump instruction. Jump K. I'll call the name. The name to me is let's say Priyam Rao. Priyam Rao. You tell Priyam Rao. Jump K. Priyam Rao. Are you there or not? Priyam Rao. Priyam Rao is not there. So remove home meeting. Please put a red mark on Priyam Rao. Okay, Pritam Anand. Are you there? Pritam Anand.
Yes, sir, I am there. Sir.
Please. So come in video. Please explain this.
Sir, I don't know, sir.
You see the manual which I have sent. What is jump K? भाई ठीक से अटेंड करो क्लास, नहीं अटेंड करना है तो मत करो, सो जाओ. You are actually unnecessarily wasting everybody's time. Actually, the network time. Rahul Ranjan, can you explain this? Rahul Ranjan, are you there?
Yes, sir.
Please see the manual and tell me. Please come in video.
In description there is jump and
Yeah.
from K to PC
Yes.
operation.
Yes, very
And
good.
sir, clock cycle is 3.
I'll explain. I know.
Okay.
So jump K is a number. It is actually an address. So gem is jump. What is jump? That means you are writing code 1, code 2, code 3. But suddenly you are writing jump some number K, 16-bit number. So it is going to. So these codes, the add, subtract, multiply, whatever you write. So these codes are loaded where? It is loaded in some address location. Address AD, address 1, address 2, address 3, like that. So they are all 16-bit address. If you look at this, your architecture, this flash program memory is basically a memory like this. It has got some locations. Each location is of addressing is 16-bit. So program counter points to this address. That means it is having one code, then next code, like that. So by this jump, what it does, that means if the program counter will be replaced by this K number. You can see PCK, that means this program counter will be replaced by K. This K will come to PC. So that means the code will start working from this K location. Whatever code is written, it will be decoded. Are you getting my point? That means program branch change. It is called branch instruction. On conditional branch instruction. So K is a 16-bit number. So total clock cycles is 3 cycles. Because the K, you have to read this 8-bit, then 16-bit. After reading, then K will be replaced with counter. So that takes 3 cycles. Is it clear to you guys?
So like if we write this, like generally we write this jump instruction at the end of any function, or like in between loops also we can write this.
Yeah, you can write in between loops also, yes. You can have jump and conditional jump. We'll see conditional jump later. So this is just jump. Jump means no condition. It will just jump. It will branch. Right.
So if I write the jump in between a loop, then it will go to that particular branch. Then
Yes.
the
So
instruction.
even if the instructions are here, nothing will be executed. It will go to K directly. It will skip this. You got my point?
Okay.
So like then what is the difference between RJMP and JMP?
I'll come to that. Don't worry. Yes, very nice. Okay, so now we'll discuss about this R jump.
Sir, why jump takes 3 clock cycles? Shouldn't it take only 2 clock cycles?
K is a 16-bit number. So when you store this number, it will be in 3 bytes, not 1 byte. Like add R1, R2 is 1 byte. So this is a 3-byte instruction. So you have to read these instructions one after the other. First you read the mnemonic, that is JMP. First one is mnemonic, that is JMP you read. Then you know that you have to read another 16-bit number, 8-bit at a time. So you have to read these 2 numbers. So therefore it takes more than 2 clock cycles.
Okay, sir.
Got it? So this class is very important, guys. So R jump K. If you look at R jump K, please look at R jump K. So K is 8 bits. So it is called relative jump. It is called relative. Manav Nitin Kapadis. Manav Nitin, are you there? Manav Nitin. Pooja, please put a red mark. Manav Nitin. Okay, Devendra Praveen, Sankecha.
Yes, sir.
Okay, very good. So can you come in for R jump? Read whatever is there. Please put your video on and then tell.
Yes, sir. R jump, no?
R jump.
Yes, sir. It is relative jump. T from
Relative
PC
jump.
to.
So this is a 8-bit number. Okay. So what will be the instruction size here? This is a number and this is the mnemonic. What will be the instruction size? How many bytes?
Hello.
How many bytes will be the instruction approximately?
I think, sir, 8 bytes because it is taking only 2 clocks.
No, not because this is a number and this is the mnemonic. That means this is 8 bits, this is another 8 bits. So total 2 bytes. Okay.
Okay, sir.
So what relative jump is with respect to the program counter, it will jump. Like PC will be added with this K plus 1. This is called relative jump. So what is the advantage of relative jump? Anybody who can say that means it will jump with respect to the present location 255 plus minus. 250,
Sir,
255.
sir, could you please explain that why jump has 3 bytes and R jump has 2 bytes?
This is 8 bit. Jump K, this is 16 bit. This is 16 bit. So this is instruction code 8 bit already. So this is 8 bit, another 8 bits. So 3 bytes. Byte 1, byte 2.
Okay, sir.
Byte 3. So they will be stored in 3 bytes of memory. Memory is a byte memory. So you have to read all these 3 bytes. So first you read the jump code, then 2 numbers, 8 bit numbers, 16 bit. So then that's why it has to read 3. Here it is R jump K means only 2 bytes. So it will read 2. So there will be instruction read 2 cycles. So it will execution will be in the same cycle. So it will be a 2 clock cycle instruction. PC is PC plus K plus 1. So this is R jump. Similarly, there is one indirect jump, I jump.
Hello, sir.
Yes.
Sir, then the add operation that should also take 3 clock cycle, right?
Add operation not 3 clock cycle. Add R1, R2, 1 clock cycle. Because this whole thing is only 8 bits. The code is 8 bits. So it is 1 clock cycle. We'll read about this coding of instructions, don't worry, binary coding, how it is coded.
Sir,
Yes.
Is this Manav? Like you called my name, and by the time I could unmute, someone removed me from the meeting.
I removed you from the meeting because you didn't respond. Okay, so be careful. Next time, if you repeat it 3 times, if I call you don't respond, then it will have a very bad impact on your grading. I'm telling you.
Sorry.
Suppose you get 78. Okay, I will not make it A grade. But if you have this kind of, I will not give you this to. I will not punish you, but I will not reward you. That is what is my commitment. If you guys are not sincere, not listening to me, if you keep 79, you'll be 79. I'll not make it 80.
I heard the question. Like you asked what.
That's okay. This is first time, but 2 more times. 3 times if you get a red mark, I am requesting my TA. So that means you are in trouble. Be attentive to the class because I have no control on you, right? If you had been in front of me, you had been automatically attentive. But this is natural because online class nobody cares. Okay, so I jump is relative jump. What happens? There is a Z register. Who can tell me about Z register? Namrata, can you tell me? Kadashi Namrata. Are you there, Namrata?
Yes, sir.
Can you tell me about Z register?
I think it is the 0 register.
No.
No.
Please check. In the 32-bit registers, what is the Z register?
So 0 flag register.
No. Z is anybody who can answer, please raise your hand.
A temporary 8-bit register.
No. Raise your hand who can answer this. Yes, thank you. Shubham, please answer.
Sir, it is a 16-bit register made up of 2 GPRs, 2 general purpose registers. So it acts like a pointer. It points
So
to certain
which
location.
2 registers make Z register? Please find out and tell me.
Yes, sir, I need to check it.
Let's find out. There are 2 registers which make. अरे भाई आप लोग पढ़ोगे नहीं तो मैं कैसे? I cannot help you guys.
R30 and R31.
I think so. You please find out R30 and R31. I think. So these 2 registers make Z register. या दूसरा फाइल. Let me give you the register architecture once again. Please remember this, okay? This one you please remember.
Sir?
Yes.
Sir, hello.
Yes, please tell me.
So like I actually didn't understand like properly the difference between RJMP and JMP. Like, can you show an example to like differentiate like?
Yeah, examples will be following. Don't worry about the examples now. I will be giving lots of examples. See, when you are in the program, you are writing codes like add, let's say add R1, R2, subtract R3, R4, like that. If you write, suppose you write RGen. Okay, this is 8-bit number. So it's a program counter. This comes to, let's say, FF00, one address. So this becomes FF01. This becomes FF02. Suppose you write rjump 32. So program counter has this FF02 now. Is it clear to you? When you get this instruction, then what will happen? So it will have two locations, rjump and 32. FF03 will have this 32. So then program counter has FF03. Because it's getting rjump 32. These two codes, this is 16-bit code, 8-bit, 8-bit. So this will be added with 32 plus 1. So new program counter. New program counter address will be FF03 plus 32 plus 1. 32H. Let's write all these hexadecimal numbers. Hexadecimal. But instead of rjump, suppose you would have put jump. If you would have been jump, then there will be a 16-bit number. Like jump, you can write 3051 or 305C. So this will be 5C, this will be 30. So then the program counter would have been totally replaced with 305C. So one is relative, one is absolute. Could you get it?
Yes, sir, yes.
So I'm giving you the register architecture. Please remember this. Don't see, you have to do coding. You have to do in real time. You have to also prove this it is working. So here you cannot, you have to be there. So without that, you cannot pass in this subject. You not get a good grade. Passing though is not a problem. P grade is not an issue for you. You see. So which is Z register? This is low byte, that is 30, 31 is high byte. So Z register means you can write like this, R30 colon R31. They are together. Sorry, not like this. Z register is R31 colon R30. This is how. This will be high byte, so 16-bit register. So this indirect jump, Z is a 60. So the Z will come to program counter. That is indirect jump. I jump. I jump means this instruction will do what? The Z value will come to the program counter. Is that clear to you?
Sir, what is use of iJump?
Sometimes you want to keep the address not in the program. You can just keep in the Z address, Z register while manipulating. It will be useful because address, if you would have given jump a particular address, that you cannot change. This address you cannot change. This will be fixed in the instruction. But if you change Z, your address will change. So that's why iJump is very little flexible. Is that clear? Is that clear?
No, sir.
iJump is what is the difference between jump and iJump? Jump JMP, you have to give a 16-bit number like 301C hexadecimal. So this is a part of the instruction. You cannot change this. 301C means 301C fixed. But if you write iJump, what happens? So basically, this will be always the program counter will be replaced with 301C. But in iJump, program counter will be replaced by the Z register, and you can manipulate Z register by your code. So therefore, it is little flexible. Are you getting my point?
Yes, sir. Yes, sir. Got it.
So like this means like if I store a value in the Z register and I write iJump Z, then it will go to that address which is equal to the value stored in the Z register, right?
Exactly. Right. Yes, absolutely. So now let's discuss about call. There is a difference. A call means where it is associated with subroutines. Okay, so let me tell you about a little bit of subroutines. We'll come back to subroutines. So you'll write delay subroutines when you want to write. So we'll talk about delay subroutines. So call instruction. For example, call a 16-bit number K. So it will just like jump, but only thing is there will be use of stack here. Stack we'll discuss is an area of the memory which is reserved for stack, and the top of the stack address is given in the stack pointer. There is a stack pointer in that register profile. If you look at the register profile, there is a stack pointer. So when you do the call instruction, what will happen? Suppose there are you write codes like this add, subtract, etc., and there is a call instruction. So this has some memory like this 301. They are hexadecimal numbers 302. So call instruction will have 303 followed by 2 more because there are 2 bytes. Call K. K is having 2 bytes. It's a 16-bit number. So 304, 305. So if you call a subroutine, what will happen? This 305 from which it will branch, this number address will go to the stack. This stack will come like this 05, 3. The stack pointer will be automatically implemented. So when you go call, then in the subroutine, after executing, there is a return instruction. When you do return, this address will be reloaded into the program counter. So call means it will go when you return the program counter earlier track of the address. This address 306, next address will be automatically there. So call return automatically comes back to the same location. That means you can branch from a program and come back to the next location. Is it clear to all of you?
Sir, can you explain this part again, just the last?
When you do jump, what will happen? It is gone. Jump K means it is gone, it will never come back. So this is address, this address is gone. You cannot come back to this. But when you do call K, so call K, suppose you are in address and the next instruction is something like R1, R2. So call K address 1, address 2, address 3, 3 addresses. So then it goes to the next address, address 4. So the moment you do the call instruction, so the call instruction occupies 3 addresses because call and a 16-bit number. So what will happen? It will go to the branch kth place. Program counter will be replaced by K, and the subroutine will be executed. If there is a return instruction, what will happen? Automatically during call, this address will be pushed into the stack. When it will experience a return instruction, it will be popped again. That means when you return, you come back to the earlier program, next location, next instruction, which doesn't happen in jump. So call instruction is specifically for calling subroutines. You are in the main program, you are executing, again call branch, then execute the program, again come back to the next address. So this is how, this is call, this is return. But if it is jump, there is no track to come back, not possible. And while calling, the next address is loaded into the stack. Is it clear to you guys?
Sir, it will come back to address 4, right?
Yeah, next address. These 3 addresses will be called. The next address will be the next instruction. It will come to the next address. So this address plus 1 will be saved into the stack pointer. Stack. Okay, not stack, but stack. This is call.
Sir, can you explain its clock cycle, number of clock cycles, like 4? How is it?
Obviously, there will be call instruction. There is a branch and there is a pushing into the stack. So there is one additional thing which does where pushing the next address into the stack. Therefore, this is 4 clock cycles. Call itself is 3 bytes. Call a 16-bit number. It is a 3 byte. So again, you have to push it back from the stack. Similarly, return is also again popping it back to the stack to program counter. It is also 4 cycle. It will branch again, come back. So all the call and return, they are 4 cycles.
So return is 1 byte. That's why total we are needing.
Even if return is 1 byte, it has to come back to the previous location. Program counter has to be loaded by 2 more bytes. So there will be 2 popping up instructions. So call and return will have similar thing, 4 cycles each. Okay, that's how it happens. Return is also branching out. Program counter call, what happens? Program counter will be replaced with K and it will be pushed into the stack, next address. Return is program, it will be popped back, again pushed into the program counter. So both are 4 cycles. Similarly, there is iCall. iCall means the Z. iCall means just if you write iCall, program counter will be replaced by this Z register, whatever is there in the Z register. So this is iCall, but same push instruction will happen into the stack. So this is called iCall. So like this, there are lots of instructions. So what you guys you are requested to do is, I'll just discuss few instructions. So there are branch instruction, conditional branch instructions, for example. Let me just give you that example from conditional branch because this will be very handy for you. So I'll just give you the conditional branch instructions. So your job is to go through these instruction profiles. Then we'll write assembly code. So let me just expand a little bit and we'll talk about these branch instructions. So while writing codes, you keep this. This is about how many pages? Page 1, 2, 3, 4. About 4 pages. So these 4 pages you keep in front of your code, in front of you. Just take a printout and keep it. It will be easier for you. So if you look at these instructions called branch instructions, this tells you BRBSSK, branch if status flag is set. Okay. So S is one of the status. Status can be carry, Z, many things. Okay. So this says that program counter will be replaced by program counter plus K plus 1. K is, so this is a relative branch instruction. And the number of clock cycles, it is 1 cycles in advanced microcontrollers, 2 cycles in ordinary base level microcontrollers. That's why it is then 1 plus 2. Okay. Then BRBC, branch if status flag is cleared. BREQ, branch if equal. BRNE, branch is not equal. Branch if not equal. Branch if carry flag is set. So BRCC, branch if carry is cleared. So all are relative. So these are called conditional branch instructions. Branch if plus, branch is greater or equal. So these are all branch if overflow. So these are all relative and the program counter is replaced by program counter plus k plus 1. So this takes 1 clock cycle in advanced microcontrollers, 2 cycles I think in base level microcontrollers. What you are using is a base level microcontroller, so it will take 2 clock cycles. So these are different branch instructions. Then load store instructions. So let me just go through these instructions. For example, move. Move I have told already that 1 register to another register and 1 clock cycle. Load immediate, 1 register will be loaded with some value. So this is 1 clock cycle, 8-bit value. LDS, load direct from static RAM. Static RAM is the data memory. So it will load from, so it will take 3 clock cycles. Then load indirect, load RD plus post increment. That means after loading, X is the address. So after loading this from the address X, it will be incremented by 1. Then load RD minus X, load indirect pre-decrement. So these are useful for loops, executing for loops, etc. When you translate program from C to this, so load, similarly there are store instructions. So today I shall finish here. So I shall request each one of you to go through these assembly language instructions. On Monday, we shall write some codes. We will find out and debug some codes. In the meantime, in the assembly language, AVR assembly language user guide, you will find there are many things like how to load this. So have you been given demonstrations about Patida? They have got the demonstration for assembly language coding? Puja or Patdavan, are you there? Hello? Puja, Patidavan, anybody is there? Or anybody who can tell me from the students, have you got the demonstration on assembly language coding? Harsh Singh? Harsh Singh,
Yes, sir.
yeah. So have you got a demo on assembly language coding?
So we were given a sample code, but not exactly the demo.
Sample
We were
code
not explained. We were not explained. Like,
Okay.
we were just shown the code. Sir, you're muted.
But any TA is there?
Hello? Hello?
Yes, Puja.
Yes, sir.
Puja, any demo has been given? Otherwise, ask them to give a demo on Monday. Okay.
Okay, sir. Okay, sir.
Assembly language.
Sir, we have just shown the code only. We have not given the demo.
So that demo has to be given. So let's give a demo. All right. So tomorrow in the lab will be that is afternoon, Wednesday afternoon. Okay. So come prepared to the lab with your devices. So we'll do it. So take the attendance, Puja. Okay.
Yes, sir. I have taken.
Thank you very much. Bye bye.